Very good morning, children. In the solid state chapter, there are the possibilities to have one objective type question for this NEET examination. First thing is you must read the NCERT textbook point to point. And once we start reading this NCERT textbook point to point, we will come across the starting about the differences between crystalline and amorphous. Differences between crystalline and amorphous. Once you see this crystalline and amorphous, the small points that will be questioned from this area is these are having short range order. Amorphous are having short range order, and they are isotropy in nature. They are isotropy in nature. Means when we draw from any plane, the similar type of atoms or ions or molecules will be observed. But the crystalline have long range of order. Long range of order. Means the arrangement will be in a repeated manner. But they will show anisotropy. Means if you draw from different planes the angles, so this is what anisotropy means. Once you see the atoms or molecules or ions here, atoms or molecules or ions, if you draw a line using this plane, you will come across one set of atoms like A, B, or if you draw only one line like this, like the line AB, A to B, and C to D, we will see. In the A to D there are only one set of atoms, whereas in the C to D there are different set of atoms. Whereas their refractive index will be different. So these points they will be completely different from each other. The amorphous, once you see this is having the examples like glass, rubber. What else we have? Very simple examples, right? Plastic, glass, rubber, plastic. This all comes under the anisotropy. And remaining most of the solids like ionic compounds comes under our crystalline solids. Now we are going to see how are these crystalline solids classified. How are these crystalline solids classified? We know the classification of these crystalline solids. Classification of crystalline solids. Is again further given in textbook very in detail. You can please go through this one. They are first of all classified as the molecular crystalline solids, which are having further types as polar molecular solids, non-polar molecular solids, and they are having the hydrogen bonding. They are having the hydrogen bonding type of molecules. Or you can see the second one may be the ionic type of crystalline solids, you can see, or you can see the metallic type of crystalline solids, or you can see the covalent crystalline solids or the network type of crystalline solids. So this all area was given in the form of tabulated data in the form of textbook. Please go through that area. So after these, what are the next areas we are going to see is about the unit cell. What is an unit cell? What is an unit cell? You know that the unit cell is having all the edge lengths what we got in the PUC, but we are not going to waste our time to deal in detail the crystal lattices, that is called as the crystal lattices. From these crystal lattices, the simple questions will be given like how many space lattices are there? See, before we go for the space lattices, the crystal lattice or the unit cell, there are of two types. Unit cells are of two types. How many types of unit cells are there, children? Primitive type and the centered unit type. Primitive type and the centered unit type. So, upon you see the tabulated data, edge length, A is equal to B is equal to C, A is equal to B is not equal to C, and the angles. Those are all discussed along with the examples. You please read the whole table. I cannot write and waste the time here. So based on maybe an objective question can be extracted asking the example. So based on those all, we have the spaced axis completely of 14. These are also called previous axis. And now followed with this, we say the centered unit cell. What do we call as the centered unit cell? What is meant by called as the centered unit cell, children? Centered unit cell. This is the primitive unit cell that you can see. First of all, I am drawing the primitive unit cell. In the primitive unit cell, the atoms or ions are present only at the corners. In the primitive unit cell, atoms or ions are present only at the corners. And here, in the simple cubic unit cell, this is also called as the simple cubic unit cell. In the simple cubic unit cell, the points to be remembered are, this is what we call as the edge length. From here to here, what do we call as the edge length? Once we see in detail, the edge length, the two atoms are present on this edge length. How many atoms are present on this edge length? Two atoms are present on this edge length. Here we are representing as R and here we are representing as the R. So how is the edge length given in the simple cubic unit cell? The edge length A is given as 2R. Or the radius, we can also write as radius R is equal to A by 2. Radius is equal to R is equal to A by 2. But I am introducing one word here, distance between neighboring atoms. Distance between the neighboring atoms. This is the word that is very important for the objective. It is generally represented as symbol with D. The distance between the neighboring atoms is nothing but how much is the distance between these two atoms that are separating. How much is the distance here? It is equal to A. But we know, what do we know? D is equal to edge length A is given as the 2 into R. So the distance is equal to 2 into R in case of simple cubic unit cell. So this is what, just to introduce, what are the points that will be covered in a simple cubic unit cell. These are the three main points that will be covered in a simple cubic unit cell. You already know the number of atoms present in the simple cubic unit cell. Generally, we will be forwarded to calculate the formula of a compound. When we are going to see the formula of a compound, after this concept, there are some points to remember. What is the part of atom? On the corner, the part of the atom is 1 by 8. Means on this corner, the part of the atom will be 1 by 8. Face centered. What is the part of the atom on the face centered? Face centered part is the half. On this edge centered. Generally we call it as the edge centered. That is given as the 1 by 4. And we are very well familiar as the body centered. Body centered is 1. So here only the simple cubic unit cell. In the simple cubic unit cell, atoms are present only on the corners. So these are the main formula that are very important in regarding the calculations regarding all these types of unit cells. So please write down 1 by 1 unit cell. I will recall once again. So those things are very useful in finding the formula of the compound. Let me give you one question on the board about the formula of the compound. Before I go to the formula of the compound, there is a small concept still to be recalled. For example, we know what is meant by a void. Void is the space between the two atoms or the molecules. Void is the space between to atoms or molecules. We are not working with theory, so I am not going in depth now. Here, for example, we are going to represent number of voids in the octahedral and tetrahedral compounds. How are they given? Tetrahedral compounds, how are they given? In the octahedral, the number of voids are given as octahedral type of compounds, number of voids are given as the n, whereas the tetrahedral, number of voids are given as the 2n. Number of voids are given as the 2n. In solving the compounds, like for finding number of atoms, when we work with in finding number of atoms. In the case of simple cubic unit cell, how many number of atoms are there? How did you got this one? Do you remember, children? In the simple cubic unit cell, 8 corners are there. Part of the atom on the corner is 1 by 8. So 8 into 1 by 8, we got as 7. And in the case of face-centered cubic unit cell, how many faces are there? 6 faces are there, and each part is half. So there are 3 atoms, and on the corners 8 corners are there. 8 into 1 by 8, we have 1 atom. So in the face-centered, total number of atoms are the 4. How about the number of atoms in the body-centered cubic unit cell? In the body-centered cubic unit cell, at the center, body center, there is 1 atom, and 8 corners are there. 8 into 1 by 8. So we got as the 1 atom. So in the body centered, total number of atoms are 2. And now we had learned the word packing efficiency. What words had we learned? Packing efficiency. So before we go to the packing efficiency, one small point you must not forget. The packing efficiency. Once you see, it is started with face-centered unit cell. What is it? Started with the face-centered type of unit cell. So face-centered type of unit cell, it is generally represented as the FCC or CCP or HCP. These are given as the FCC or CCP or HCP. In the face-centered type of unit cell, how many number of atoms are there, children? In the face-centered type of unit cell, the total number of atoms are 4. When you are working with the problems related to finding formula of the compound. Whenever you are working with this formula of the compound, they will mention the atoms are occupying the octahedral voids. Or the atoms are occupying the tetrahedral voids. How is the octahedral void filled with which type of arrangement? Means octahedral void will be filled with the type of arrangement called SCC, means face-centered cubic, or CCP or HCP. What we came to know is octahedral voids, how are they represented as the n? So its Benton value will be equal to the number of atoms present in FCC type of arrangement. Is equal to the number of atoms present in the FCC type of arrangement. In that, how many atoms are there? 4 atoms are there. Whereas in the tetrahedral voids, these are being filled with the BCC type of atoms. Here, how is the tetrahedral void? Number of voids, tetrahedral voids they are represented as the 2n. Or they are represented as the word 8. Or the number as the word 8. So don't forget, when you are working with the formula of a compound, you must not give up this point. Octahedral is represented as the n. In the octahedral type of arrangement, which will be occupied as FCC or CCP or HCP will be there. So n value will be equal to 4. So these are the very simple points. So let us see one problem on this, how do they will be giving, then we can go forward. So regarding this, I had written one question on the board, writing the formula of a compound. Let me read the question, then I will explain the concept to you. Structure of a mixed oxide is CCP. Structure of a mixed oxide is CCP. The cubic unit cell of mixed oxide is composed of oxide ions. The cubic unit cell of mixed oxide is composed of oxide ions. 1/4 of the tetrahedral voids are 1/4 of the tetrahedral voids are occupied by the divalent metal A. Occupied by the divalent metal A. And the octahedral voids are occupied by the monovalent metal B. Monovalent metal B. The formula of oxide is option A AbO2, option B A2B2O2, option C A2B3O4, option D AB2O2. See children, whenever a question is given, first you see the options. What you can see from the options means you can study ABO is there. From the question what they had given, structure of mixed oxide is CCP. Structure of mixed oxide is CCP. So mixed oxide structure is equal to CCP. What we had already learned, CCP or FCC or HCP. How many number of atoms will be there for them? 4 number of atoms will be there. How many number of atoms will be there? 4 number of atoms will be there. The cubic unit cell of mixed oxide is composed of oxide ions. Means this CCP is being occupied by oxide ions. CCP is being occupied by the oxide ions. That is O-2 ions. It is being occupied by the O-2 ions. 1/4 of the tetrahedral voids are occupied by metal A. So this is regarding the oxide ion. How about the metal A they are saying? Metal A. Where is the metal A occupied they are suggesting? Metal A had occupied 1/4 of tetrahedral voids. A is occupying 1/4 of the tetrahedral voids. And metal B, where is the occupying? Octahedral voids are occupied by the metal B. So metal B is occupying the octahedral voids. Where is the oxygen occupying? Oxide is occupying the octahedral. Oxygen is occupying the octahedral, that is equal to 4. What do we know the data? Tetrahedral, how is it given? 2n. N is generally 4. N is generally 4. Don't go with any other options. Octahedral means n. N is equal to 4. This n is equal to 4. Here A, I am saying 2 into n. N is equal to 4 every time. N will be equal to 4 octahedral. So 2 into n. 2 into n, or I can say 8 into 1/4. 8 into 1/4, how many times will we get? 8 into 1/4, B is equal to 4 and C is also equal to 4. So please solve this one, then you can help me. How are you getting this one, children? What is the formula you are getting in this? A is 2 A2 B4 C4, or we can express A B2 C2. This is the method how to work with this type of problems. Where is this one? A B2 not C2, that is oxygen. Third one is the oxygen, I written as C. So in this method we will work with these problems. Let us see the next important concept about radius ratio. So let us see here about one word, radius ratio. There is a new concept for us. Radius ratio. It is not in our PUC syllabus. Radius ratio, but it is very important for the objective. Very important for the objective. What is meant by the radius ratio? It is the ratio of radius of cation to the radius of anion. Radius of cation to the radius of anion. Radius ratio is the ratio of radius of cation to the radius of the anion. Generally, cations will be very small, whereas the anions will be somewhat large. Anions will be somewhat large. So, what do these cations will do? These cations will occupy the void. These cations will occupy the void, means the empty space, whereas the anions will be in the form of the spheres, or in the form of the circles. In the form of the circles. So that is what useful in the next point of view. By these in this area there are some objective questions being asked, but there are some already calculated radius ratio values given for us based upon the coordination number of the given compound. Based on the coordination number of the given compound. What is meant by the coordination number? What is meant by the coordination number? In the one-dimensional array, if I consider one atom, to this, how many are directly bonded? Two atoms are directly bonded. It is called as its coordination number. It is called as its coordination number. So, the number of atoms that are directly bonded to a particular atom is called as the coordination number. In case of sodium chloride, each sodium will be covered with 6 of the chloride ions. Each sodium will be covered with 6 of the chloride ions, as well as each chloride ion is surrounded by 6 of the sodium ions. 6 of the sodium ions. So what we can speak here means the coordination number of sodium means how many chlorines it is covered? It is covered by 6 chloride ions. Parallelly, what is the coordination number of chlorine? Each chloride ion is surrounded by 6 of the sodium ions. So, this is what we speak. The sodium chloride is having a coordination of 6:6. Coordination number of 6:6. So, first thing is we are seeing about the coordination number. This type of coordination numbers we are going to see. How many coordination numbers we are going to see? Coordination number 3, coordination number 4, coordination number 6, coordination number 8. In this case of this radius ratio, the range is 0.155 to 0.225. Means the radius ratio, when this is in this range, coordination number will be 3. Coordination number will be 3. It is called as of a trigonal planar type of arrangement. Planar type of arrangement. Trigonal planar type of arrangement. When the radius ratio is of 0.225 to 0.414, the coordination number is called 4. And they will show the shape called as the tetrahedral arrangement. What kind of arrangement they will say? Tetrahedral arrangement. When the radius ratio is 0.414 to 0.732, they will have a coordination number of 6. We will say it is of octahedral arrangement. It is of octahedral arrangement. Here the examples are, it is of the type B2O3 and it is of the type zinc sulfide type. It is of the sodium chloride type. Most of the problems will come across in these areas. Sodium chloride type, these are all examples. So, in the examination point of view, they can ask it is showing the type of arrangement. What will be the radius ratio? What will be the radius ratio? Let me give one problem that you can clearly understand. If the radius ratio is ranging from 0.73 to 0.73 to 0.1, then the coordination number will be 8. It is of the cubic type of arrangement, and we say it belongs to cesium chloride type of example. Cesium chloride type of example. So this is what one of the new area that we didn't cover in the PUC. Right now, children, after seeing one problem, you can clearly understand this one. Okay, children, let us see here one question regarding the radius ratio value. A solid compound XY has NaCl structure. A solid compound XY has NaCl structure. If the radius of cation is 100 picometers, the radius of anion is how to work with this type of problem, student? NaCl shows which type of arrangement? NaCl shows which kind of arrangement we had seen. It will show octahedral type of arrangement. Which kind of arrangement? Octahedral type of arrangement. Don't forget the value 0.155 to 0.225. 0.225 to 0.414, 0.414 to 0.732, and 0.73 to 0.1. This will show planar triangular, and here this will show tetrahedral, here it will show octahedral, and this will show cubic type of arrangement. The coordination numbers once we see 3, 4, 6 and 8. What are the questions they have raised here? A solid compound XY has NaCl type of structure. For these examples also we have given. This will show B2O3 type of example, and zinc sulfide type of example, NaCl type of example, and cesium chloride type of example. The type they will give. What they are saying, it is showing NaCl type of arrangement. Then what will be the radius ratio, children? Radius ratio. What is the radius ratio? Radius of cation upon radius of anion. The initial value we will take. What is the initial value here? 0.414. What they are giving here is if the radius of cation is 100 picometers. The radius of anion will be, how much will be the radius of anion? Radius of anion is equal to 100 upon 0.414. I hope you understood how to work and how the question will be given. They will ask either the radius of cation or either they will ask the radius of the anion. Now let us see another question. A crystalline structure has radius ratio in range of 0.225 to 0.414. The coordination number and arrangement of anion around cations are 0.225 to 0.414 will have this kind of coordination, tetrahedral type of coordination. Coordination number is 4 and arrangement is tetrahedral type of arrangement. So coordination, first thing they are asking is the coordination. Coordination number will be 0.2 means 4. And the arrangement of anion around cation is 4 means compulsorily have tetrahedral. So this type of direct questions will be there, or they will be asking to find the radius of the cation or the radius of the anion. Let us continue here our concept regarding the distance between two atoms or the neighboring atoms. We had given that in the case of simple cubic, but we hadn't learned how do the distance between the neighboring atoms will be calculated in the FCC or in the PCC. So presently our work is to find out the distance between the neighboring atoms. Distance between neighboring atoms or nearest distance between neighboring atoms, we can say, or nearest distance. It is also calculated as the nearest distance between the atoms. Nearest distance between the atoms. First, I would like to give you regarding the FCC. Regarding the FCC. What is FCC, children? We know. What do we know? In the case of FCC, atoms are present on the faces. Atoms are present on the faces. This is what a crystal here. In order to identify, I am calling this one as the A, and this is as the B, this is as the C, this is as the D, E, F, G, and the H. A, B, C, D, E, F, G, and the H. Face centered cubic units. Here all the edges, all the edge lengths, they are given as A. All the edge lengths. Edge length, how do we give? Edge length, how do we give? Edge length is given as the A. What is meant by face centered? Here one atom is there on one corner. Here another atom is there on the another corner. There is an atom at the center. There is an atom at the center. There is an atom at the center. Just to encircle, I am saying for my clarification. Here I am drawing one face diagonal. We can speak face diagonal. Any face you can take. Here, what we know account to Pythagoras theorem? We know account to the Pythagoras theorem. AC square in the triangle, in triangle ABC, in the triangle ABC, ABC, AC square is equal to AB square plus BC square. Is not here, so AC square is equal to what is there from A to B? A is there. B to C also A is there. So A square plus A square. A square plus A square. So AC square is equal to 2A square. AC square is equal to 2A square. Or here in textbook we have written this one as the B. So B is nothing but the AC square. B, how do we write? Root 2 into A. How do we write it as the root 2 into A? But the problem is the length here, it is of R, it is of 2R, it is also of another R. From here it is R. So the length along the B is equal to 4R. Is equal to 4R. So we say 2A is equal to 4R, or the A is equal to 4R by root 2. 4R by root 2. How shall we write here? The 4 shall I write this one as? How shall I write the 4? Can you write the 4 as 4 is equal to 2 into R upon root 2. But what we know regarding 2, I would like to write one of the 2 as root 2 into root 2 upon root 2. So here, if we cancel root 2 and root 2, that will be written as A is equal to 2 into root 2 into R. A is equal to 2 into root 2 into R. Or how can we get R? R is written as A by 2 into root 2. A by 2 into root 2. This is edge length, this is the radius. This is edge length and it is the radius. But nothing we brought regarding our distance between the two atoms. Distance between the two atoms. See, from here to here, there are two atoms. What is the distance? It is half of the distance of. It is half of the distance of face diagonal. Half of the distance of the face diagonal. How much we got the face diagonal here? So the distance between nearest distance we can give, it is half of the face diagonal. Half of the face diagonal. How much is the face diagonal? We can say face diagonal is equal to root 2 into a half. I said nearest distance is given as the half of face diagonal. face diagonal. So half of the face diagonal we can say as the 2. Again we can write this 2 as, how can we write this 2 as root 2 into root 2. Then 2 into cancel. So distance is given as a by root 2. How is distance given as the? Distance is given as the a by root 2. So the nearest distance formula, how do we get? The nearest distance formula is given as the a by root 2. What is the nearest distance means? The distance between these two atoms. How much it is? It is half of the face diagonal. Half of the face diagonal. So based on our need, incident may be asked, radius may be asked, or the distance between the nearest atom may be asked. You must not forget the formula. Let me give you about the BCC also. Let us say the nearest distance in the BCC type of arrangement. In the BCC type of arrangement, small children, in a cube, all the corners are present. Along with the corners, one atom is present at the center. One atom is present at the center. So let us write there is a face diagonal here. This is one below face, no? Face diagonal I am calling this one as the triangle EFD. What am I calling this one as the triangle EFD? See, this is the edge length A, this is also edge length A. But here we can represent this one as the B. We can represent that one as the B. In triangle EFD, FD square is equal to EF square plus ED square. What is the EF square value? A square. What is the ED? A square. So FD square, you can write this one as the A square, or you can write this one also as the B square. Your wish. You can represent it in any of the method. So FD is equal to FD square is equal to 2A square, or FD is equal to root 2A, or we can say this is the B is equal to root 2 into A. But what we want, we are going to draw, or we want to say this is one atom at the corner, this is at opposite corner, that there above corner and the below corner, and one atom is connecting at the center of the cube. So once you see this is R, and this is 2R, and this is also R, and we are calling this one as the body diagonal. What are we calling this one as the body diagonal? Body diagonal. Now you see in the triangle AFD, in the triangle AFD, in triangle AFD, AF square is equal to AD square plus FD square. AD square plus FD square. How much is the AD value? AD value is A. Edge length is A. How much is the FD? This B. So AF square I am calling this one as the C. I call it as the C. So C square is equal to AD. How much we got? A square plus FD square. We have B square. But we already know B square value. The B square value, how much we have? 2A square. B square value, how much we have? 2A square. So A square plus 2A square. So C square is equal to 3A square. 3A square, or C is equal to root 3 into A. C is equal to root 3 into A. So the length around this body diagonal, is equal to 4R. Is equal to 4R. So how we have represented? Root 3A is equal to 4R. Root 3A is equal to 4R. And later we brought A is equal to 4R by root 3. This we used in our calculations, or we can say R is equal to root 3 by 4 into A. These are the well familiar formula for us. But our main point is regarding distance between BCC. The distance in the BCC. Means here to here we set the body diagonal around the BCC. But from here to here, how much is the distance? Here to here, how much is the distance? The body diagonal, how much had we given children? Body diagonal, how much we got? It is equal to root 3 into 8. From here to here, we get root 3 into 8. But the distance between the two atoms, distance between two atoms in BCC, means between these two, it is the half of the body diagonal. It is the half of the body diagonal. Half of the body diagonal. So the distance, how we have given? Root 3a by 2. Distance is given as the root 3a by 2. Half. Any length FCC we have taken, in the face we have taken there root 2a by 2. We also have taken root 3a by 2. Means only half of the distance we are taking. The half of the distance is called as the distance between the nearest neighboring atoms. Distance between the nearest neighboring atoms. On this type, very important questions are here. So write down the formula. Some people are finding difficult in deriving the formula. So once I have derived, let us see one numerical on this one. See this type of question, children, here. AB crystallizes in body-centered cubic unit lattice. AB crystallizes in body-centered cubic unit lattice with edge length A equal to 387 picometers. The distance between oppositely charged ions is or the distance between the nearest atoms we can speak. How to calculate the distance in case of BCC, children? In case of BCC, root 3a by 2. Is it not? The distance of separation we have learned. In case of BCC. So 1.73 to root 3 value you know. And what is the edge length given? Edge length is given as the 387 picometers upon 2. So once you solve, you can get the answer. Very easy. The only thing is you must know the formula and you must remember the distance between the two atoms. Let us see one more problem. Let us see here, children, the one more last in this FCC and BCC type of arrangement. Regarding FCC, what you had learned about edge length, it is equal to how much? You find out. In the case of the FCC, normal edge length is very easy to find out. But in it, again they will ask ionic type of crystal. In that point of view, edge length, how to calculate? Ionic type of crystal means what? The crystal is having ionic compound. How is an ionic compound formed? So, cation and anion. It is a contribution of cation and the anion. So, in that kind, for FCC lattice of ionic crystal of sodium chloride type, the edge length how to calculate? Edge length is calculated as edge length is equal to 2 into radius of cation plus radius of anion. Similarly, for the BCC having ionic crystal, the edge length is calculated as root 3a is equal to 2 into radius of cation plus radius of anion. In this session, I am going to give only about the numeric based upon how to calculate edge length of the NaCl type. See the question here. The edge length of sodium chloride unit cell is 564 picometers. This is the A value. If the size of chloride ion is 181 picometer, the size of sodium ion is, see here in the case of FCC of the ionic crystal, how to calculate the edge length? 2 into radius of cation plus radius of anion. Or you can take it just like 2 into radius of cation plus radius of anion. See this plus some are able to see I am writing in the different color. It is equal to the edge length. We know the edge length. How much is the edge length here? Edge length is the 564 picometers. And radius of chloride ion also we know. How much is the radius of the chloride ion? Radius of the chloride ion is 181. What we don't know? We don't know the radius of the sodium ion. So radius of the sodium ion is equal to. So the two we are bringing by 564 minus minus this R value being on right side is getting subtracted. So 181. So you get it done and find out the correct option in the given options. So this is how, see, we know only about edge length in FCC and radius in FCC, but in today's sessions what had we learned? We had learned the distance or separation between the two anion and the cation, and also we had learned how to see the edge length in FCC having the ionic type of crystal. We will see the remaining topics in the next class. Thank you children, have a nice day.